Hello and welcome. In this video, we'll be discussing several examples of performing an analysis of variance. So let's get started. For our first example, we'll be looking at battery life. We're studying this hypothetically as a company who's trying to determine which battery brand to include in its products. So we're not a battery selling company, we're a company that purchases batteries to include in the products that we ship. Ideally, we'd like to use the longest lasting brand possible. So we're going to be comparing three brands of batteries, D, E, and G. We're going to test these in 5 different products each, and we're going to see how long this lasts until the battery ran out. We're going to be provided the number of hours the product was used until the battery died, and we want to use the information to answer the question, is there a difference between the average battery lives for these 3 batteries? And we're going to be doing the alpha equals 0.05. For our factor, that's our categorical variable, we're going to be looking at battery brand and thinking about the independent versus dependent variable. Think about we're trying out different battery brands to see if they cause longer lasting life. So we're trying to not necessarily manipulate the battery brands a little bit. We can randomly assign the products to the different brands, so we can control that. But what we're going to ultimately do is try to determine, do each of these battery brands yield longer lives? So the cause would be the battery brands, and the effect would be longer life in the product. So our factor, the categorical independent variable, is our battery brand. The levels are D, E, and G, the different options that that categorical variable can take on. The experimental units, the EUs, are the products. So why products? Well, we're testing it in 5 different products. We're going to have 5 products in each battery brand. And the dependent variable is going to be the hours it lasts. So our data are provided here. I have 5 observations for brand D, E, and G. And it's worth noting that nothing connects the first observation of D with E or with G. Those are just happen to be the first observations in those groups. There's nothing more in there. I also provide the sample mean and variance. I'll say that this is not necessarily provided in your homework. I provide it here to ease hand calculation, but remember in your homework we'll be doing software, so you'll be allowed to do that, and you won't need to worry as much about the hand calculation. I'll say if you wanted this in something like your homework, I would put this in a software like R and quickly find the means and variances for each group, and then you can follow along like normal with the notes. So for this situation, our null hypothesis would be that the mean of brand D and the mean of brand E and the mean of brand G, the mean number of hours that the batteries last in these products, are all the same. Our alternative hypothesis is going to be that at least one battery brand has an average that's different than at least one other battery brand. So for our approach, we're comparing more than 2 groups on an average for a on an average for a continuous outcome variable. And that's a good indicator that I'm using my ANOVA analytic approach. In this case, when I'm using an ANOVA, the goal is to build out the ANOVA table so that I can perform my hypothesis test. So once I know I'm in ANOVA, I know I'm going to have to write and fill out this table. So it's sometimes easy to just go from left to right. And once we fill out the first column, actually, the rest of the calculations aren't too hard. So I'll start by finding the sum of squares treatment, or again, the other notation, sum of squares between, the sum of squares error, again, the other notation, sum of squares within, and the sum of squares total. And I'll say, I'm going to stop lawyering up on the notation. So make a note to yourself if the differences and the alternate notations are confusing. It's not my goal to confuse you. Both are just very, very, very common and very common to see. So I'll start just using what I have in my lecture slides. So I'm going to start there and then move from left to right. Again, it's important to be familiar with what the notation means. So as I talk through these equations, again, this is a somewhat notation-heavy chapter, probably our heaviest one notation-wise. So don't hesitate to turn back in your notes to follow along. For the sum of squares treatment, we're going to first find y dot dot bar. Remember, that's the grand mean. Now, it's worth noting that there's a shortcut formula that I didn't show you earlier. I'm showing it to you now. It's a secret. In a balanced design, and what a balanced design means is just that each of the groups has an equal sample size in each group, which is kind of what our equations were assuming earlier, but that's not always the case. In fact, it's somewhat rarely the case. In any case, in a balanced design, meaning each of the groups, brand D, brand G, brand E, all of the same number of observations in each, I can find the grand mean by just taking the average of the group means. So I have the group means on the previous slide. I just add up all the group means and divide by how many I have. I'll note that this is not equivalent to the grand mean unless the sample sizes in each of the groups are all the same. That's a balanced design. So this works for us here, and it'll work typically in this course, because typically in this course, all the groups are going to have the same sample sizes, though that's not always the case, and in fact, in practice, it's rarely the case. The grand mean is one of the sine qua nons, the prerequisites of finding our sums of squares. So once I have the grand mean, I can work now on finding the sum of squares treatment. Now, I'll mention as I'm working through these different calculations, normally what I would do if I were working on this, even if I'm using R, well, in R there's of course the built-in functions if I have data, so I don't have to do any of this. But if I'm working on like the hand components, I'd probably write out the ANOVA table and then kind of fill it in by hand as I'm working through this. So it's worth mentioning that I can't really show that easily on the slides. I'd be flipping back and forth to the ANOVA table every other bullet point. So I'm not going to do that, but it is worth noting that like if I'm doing this, I would typically have my piece of paper and then I'd find the sum of squares treatment and then I'd fill in that section in the ANOVA table. So for my equation, the sum of squares treatment, capital J, that is the number of observations in each group, times the sum over all the groups of the group mean, yi dot bar, minus the grand mean, y dot dot bar, squared. So I'm going to look at the i's, each of the groups. I'm going to take the group mean, subtract the grand mean, square that, add it all up, and then multiply by the total number of observations in each group. So I have 5 total observations in each group. Group E has 5, Group D has 5, Group G has 5. So J, capital J, is going to be 5, the observations in each group, in a single group. Then for the 3 groups, I'm going to take that group mean. For the first group, that's 70.8. For the second group, that's 80.6. For the third group, that's 70.2. I'm going to subtract the grand mean, 73.8667, from each one of those 3 numbers. I'm going to square after I do the subtraction, and then I'm going to add all those up. That's the sum. And then after I add all those up, that's when I'm going to multiply by 5. In this case, my sum of squares treatment is 340.9333 carried out to 4 decimal places. And that's my first component that I need for my ANOVA table. My sum of squares error, I do that same J minus 1 now, and then I multiply by the sum of all of the variances from each of the groups. Well, I was given the variances of each of the groups already, so this is actually a pretty easy calculation. I just add up all those variances for group 1, group 2, and group 3, and then after adding them all up, I multiply by that J minus 1. So I'm going to take 4 times that sum of all the things, and I end up getting 278.8. For the sum of squares total, I'll show you the long way and the short way, but even with the shortcut, this is a bit of the long way. So I'd have to add up all of the data values squared, and you can see I had the first 2 from group 1, the first 2 from group 2, the first 2 from group 3. I square each of those data values and then I add them up. And then at the end, you can see I then have to subtract. And in that below thing, you can see that's the division problem, that second part after the subtraction. I add up all the data values and then I square after adding them all up. And then I divide all that by the grand total number of observations. So while capital J, the number of observations in each group, is 5, the total number of observations that I have across all groups and all observations is 15 total observations. In this case, after doing all that math, I get 619.7333. This is actually much easier to do in R, but still this is kind of yucky. There is a little bit of a simpler way. Remember, the sum of squares treatment plus the sum of squares error equals the sum of squares total. So we already calculated the sum of squares treatment and sum of squares error. I could just add those together to get this outcome. So pulling the sum of squares treatment and error from my previous slides, I add them together and get that same 619.7333. Much easier if I'm doing it by hand. After the sum of squares, those are the hard part. The rest of the stuff is pretty easy. The degrees of freedom treatment is the total number of groups, capital I, minus 1. So I take the total number of groups, in this case 3, subtract 1, and I get the degrees of freedom for treatment is 2. The degrees of freedom for error is the total number of groups, capital I, times j minus 1. I do the j minus 1 first. It's in the parentheses. That's the total number of observations in each group minus 1. In this case, I have 3 groups, 5 observations in each group. 5 minus 1 happens first. It's in parentheses. That gives me 4. 4 times 3 is 12. So the degrees of freedom error is 12. The degrees of freedom for the treatment is capital I, total number of groups, times capital J, the number of observations within each group, minus 1. So that's 3 times 5, 15, minus 1, which gives me 14. The degrees of freedom treatment is total is 14. You'll notice that just like the sum of squares add up, the degrees of freedom add up too. So the degrees of freedom treatment, 2, plus the degrees of freedom error, 12, add together to give the degrees of freedom total. So that's cool for the sum of squares and the degrees of freedom, but it's worth noting the mean squares. We don't calculate the mean squares total, but if we did, the mean squares would not add up to it. So that's only the case for the sum of squares and the mean squares. We calculate the mean squares treatment by taking the sum of squares treatment over the degrees of freedom for the treatment. So 340.9333, which we found earlier, over 2, which gives us 170.4667 rounded to the 4th decimal place. The mean squares error, similarly, we take the sum of squares error divided by the degrees of freedom error. In this case, that's 278.8 over 12, or 23.23333 to 4 decimals. For the F statistic, and remember, this is the test statistic that we've done the whole table to build up to. And also remember, I'm on my piece of paper filling in each of these in the blanks in the ANOVA table. But once I get to the F, that's the ratio of the mean squares treatment over the mean squared error. So I just calculated mean squares treatment's 170.4667, mean squared errors 23.2333, and then I divide those, 170 on the top, 23 on the bottom. I end up getting 7.3372 for my F test statistic. And just like in our previous lectures where we had the test statistic for the T and the test statistic for all the other things, this is a test statistic. This is the work required. So this test statistic is a little harder to get than the previous ones, but to be fair, it's a little fancier of a test. The critical value here I calculate from R. So I'm going to use the alpha. I believe it was alpha of 0.05. I'll say for the F tests, these are all considered, I wouldn't say one-tailed tests, but we don't like cut the alpha in half or anything. We just put it all in the top tail. And for this, the degrees of freedom 1 is going to be the degrees of freedom from the numerator, and that's the degrees of freedom for the treatment. The numerator is mean squares treatment, so I pull the degrees of freedom from the treatment. In this case, the treatment is 2 degrees of freedom, so df1 equals 2. The degrees of freedom 2 is from the numerator, or excuse me, from the denominator. That's the bottom of the fraction. So if I look at my F test statistic, the bottom of the fraction is MSE, and its degrees of freedom is the FE, or the degrees of freedom for the error. The degrees of freedom for the error is 12, so my df2 is 12. After running the command to find the critical value from the F distribution with 2 and 12 degrees of freedom respectively, I get 3.8853. And again, I just calculate this using R. Given this, I can look and see the completed ANOVA table. Having filled this in on my paper, hypothetically, I'd have all these blanks filled in at this point. Maybe not the p-value, but you can easily run that on software. In this case, if I'm doing the critical value comparison, I'd compare the test statistic, 7.3372, to to that critical value, again, the F distribution with 2 and 12 degrees of freedom respectively, the cutoff 3.8853, and I can see that the test statistic is beyond the critical value. So there is enough evidence to determine that that there is a significant difference between the groups. That is, in our case, the number of hours that the battery lasts are significantly different among the groups. Which group is best would be an immediate follow-up question, but remember, that's not something that we have as part of our analysis in ANOVA. That'll be the next thing that we'll talk about in the next lecture set, or in the next lecture video, the post hoc comparisons. So once we have this, you can also use the p-value to do that rejection. Remember, we compare the p-value to alpha. In this case, our alpha is 0.05. P is less than alpha, so we reject the null hypothesis. Remember what that means. And sometimes it's nice to go back to the null hypothesis and think about rejecting like, so we've got the null and alternative. Think about rejecting like circling the null hypothesis and writing a big X through it. Writing a big X through that null hypothesis is rejecting it. So you go with the other one. So P less than alpha, I X out that null hypothesis. That null that I X'd out said all the groups are equal, so I'm Xing that out and going with the statement that said there's at least one group that's different from at least one other. That's my conclusion. When P is less than alpha, at least one of the battery brands is lasting significantly longer or shorter. Again, I don't know which direction or which brands, but something's going on here that bears further investigation. And that's what we do in the next video. And again, that's the conclusion of the ANOVA analysis. It's not necessarily a fun conclusion. It is interesting that one of the batteries lasts longer, but our application is a bit limited because we don't know where that comes from. But that is the correct end of the formal ANOVA. We then followed up with the post hoc tests. All right, so for your example, we're going to do this hours worked example comparing 6 different employees based on different locations and see if there's significantly different hours worked in the week. Now, I'll say for you, if you're doing this by hand, I pulled the F statistic here to give you the critical value for this problem is 2.6952. If you're doing this on your computer, and I mean, you're watching a video, so presumably you're on your computer, maybe you're on your phone. But if you're doing this on the computer, see as you work this one out if you can figure out how to get that F value and if you got it correctly using software. So go on and try that out on your own if you'd like. But in any case, go on, pause this video. Actually, we got to get to the data. I apologize. So let's get to the data and then you'll pause the video and give it a shot. All right, so in this case, our factor, what are we breaking down? So I think the location is related to a difference in the work hours. Maybe the location causes a difference. So the factor, the independent variable that we're comparing the levels of, is the location. The different options that location can take on, or factor levels, are Florence, Huntsville, and Birmingham. The experimental unit, who are we doing this experiment on, are the employees. Those are the units. If I look at a single number, that is an employee, their number. And the dependent variable in this case is the hours worked weekly, the average hours worked weekly for each person. All right, here we go. This is what you needed to be able to do the problem. So here's the raw data with the sample mean and the sample variance. Again, I'll read it again. The critical value for this problem, 2.6952. That's the critical F value. So go on, pause this video, give it a shot. If you've got R up, see if you can find that critical value. But pause this video, use this data, see if you can do this ANOVA analysis. We'll catch you on the other side. All right, coming back to it. Hopefully everything went well. Let's look at the answers. So for me, my null hypothesis is that the means of each of the groups, the mean number of hours worked per week in Florence and Huntsville and Birmingham, are all the same. And the alternate hypothesis is that at least one city has a different mean hours worked than at least one other city. As before, I'm going to start by calculating the grand mean, y dot bar. So y dot dot bar is going to be 52.8, all my means from each of the groups divided by 3. So I add them all up, divided by 3, I get 44.1 for the grand mean. Now I'm going to move on to finding these sums of squares, the sum of squares treatment. Here's my work. I find that to be 683.64. The sum of squares error, here's my work for this. I find that to be 223.5. And then the sum of squares total, rather than doing that big nasty equation, which you're welcome to do, I just add together the sum of squares treatment and error to get the sum of squares total of 907.14. Now that I have these sums of squares, I'm going to calculate the rest of the table. The degrees of freedom for the treatment is 3 total groups minus 1, or 2 degrees of freedom. Degrees of freedom for the error, 3 times 6 minus 1, 6 observations in each group minus 1, gives me 15 degrees of freedom for the error. And the degrees of freedom total, 3 times 6, 18 minus 1, or 17 for the degrees of freedom total. Mean squares treatment, I take that sum of squares treatment of the sum of, or over the degrees of freedom treatment, and I get 341.82. Mean squared error, sum of squares error over the degrees of freedom error, I get 14.9. Here's my work for that. The F value, this is my test statistic. I take the ratio of the mean squared treatment, 341, over mean squared error, 14.9, and I get 22.9409 for my test statistic. Again, the critical value, which I read out to you earlier, 2.6952. The first degrees of freedom are going to be from the treatment, 2. The second degrees of freedom are going to be from the error, 15. And because the F statistic is always going to be the mean squares treatment over the mean squared error, the F critical value, and when we calculate the p-value for the F distribution is always going to have the degrees of freedom 1 be from the treatment and the degrees of freedom 2 be from the error always, for the ANOVA analysis. So here's my completed ANOVA table, comparing the test statistic, 22.9409 to the critical value of 2.69. This is very significant. This is much higher than that cutoff. So we determine that there is a statistically significant difference. That is, there's enough evidence to determine that there's a statistically significant difference between the average number of hours worked among the different cities. Again, the natural follow-up question is, well, which city is higher? And in this case, we don't have an answer to that. We just know that one city is significantly better than a combination or one of the others. And so the next unit, which we'll discuss soon in the next video, is which one is higher and how can I follow up on that. In any case, in this video, we've discussed a couple of examples of how to run an analysis of variance. We worked through a couple of problems. I did one, you did one. Hopefully we got the same answers, maybe. So thanks for sticking with me through this video, and I will look forward to catching you in the next one.